For tuning in. My name is Matt Thomas, and this is the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of the presentation to take questions. So in the meantime, if you're not intending to speak, just please make sure you mute yourself and your camera's off. Jason, thanks for introducing today's speaker.
Yeah, Matt. It's my pleasure today to introduce Jeff Coes, our speaker today. Jeff is a research geologist with the USGS Landslide Hazards Program and chief of its Landslide Magnitude Mobility Project. Jeff started with the USGS in 1988 working on the Yucca Mountain Nuclear Waste Project, and he moved to the Landslide Program in 1996. Over this time, Jeff has led research and emergency response activities for just about every type of landslides, from big, slow movers like we'll hear about today, to fast-moving debris flows and rock avalanches. Jeff's research and publication records show an incredible knack for identifying important landslide problems and choosing monitoring sites to clearly reveal answers. This work spans an incredible geographic range, from way north in Alaska all the way south to Chile, from the Caribbean to the U.S. West Coast. It also includes a diverse set of natural landslide laboratories right here in Colorado. So I've learned almost everything I know about landslides from Jeff, and I'm looking forward to learning something new about a type of landslide we don't often hear about. So without further ado, here's Jeff.
All right, thank you, Jason. Well, it's my privilege and pleasure to be talking a little bit today about some USGS landslide program history at one of my favorite sites in Colorado, and that's the Bald Eagle Ridge or mountain near Leadville, Colorado. And at this site, there's ongoing ridge spreading and sagging movement. And in the title here, I call it a Sackung because Sackung in German is sagging. And Sackungen in German, which we'll talk about today too, that's just sags. So the Sackungen describes the geomorphological feature, and Sackung describes the process of sagging and spreading. What you see in this first photograph here is one of the trenches that's created by this process. On the left-hand side, you see an uphill facing scarp, which is kind of the classic type of feature that defines these features. The person there standing on the left for scale is Vince Matthews, former Colorado Geological Survey director, who has a real interest in these features and has been out to Bald Eagle at least once, I think twice, actually. This is an aerial view of the overall ridge, Bald Eagle Ridge. This is looking to the northeast. The Busk Creek Valley there is a formerly glaciated valley, had Pinedale glaciers in it. Some work by Cal Rulin and others suggests that the glaciers were completely gone from that valley about 13,000 years ago. And the relief here from the valley floor up to the ridgetop, I think, is about 500 meters. And the prominent trenches there that you see in the foreground, one of those trenches, the mid-slope trench, was the one we were just looking at on the title slide. Another example, this is the Ridgecrest Graben that's at the site, which is a pretty spectacular feature, about 100 meters wide and down dropped, just like you'd expect a classic graben would be, and it's right at the ridge crest. This is that same trench was in the title slide, and I didn't mention then, but I'll mention it now. It's 2.5 to 3 meters tall, so it's a fairly impressive feature when you run across it in the field. And this is the trench that's right above the Pinedale trim line, which I will point out here in a little bit, but it's the point that's moving the fastest in some of the surveys that I'll talk about later on. This point up on the point of the ridge there is the point that's moving the fastest. And it's also the highest scarp that we have in the study area. So what's the motivation for working at sites like this? And I really don't think it's changed much in from 1975 until now. And here are the three main things. It's just in general gain a better understanding of the development of this type of a ridge spreading. In Europe, the more common name is a DSGSD, which I still have a hard time getting out. I prefer the name Sackung or Sackung just because it's easier to say. And the surface expressions, as I already mentioned, are the Sackungen. So just gaining a better understanding of how these things work. And then, is the ridge spreading ongoing? And if so, at what rate? And is it a continuous movement or episodic? What are the forcing conditions that cause movement? A lot of these things are really appropriate. A lot of the things that I list here are really appropriate for a lot of things happening in Alaska right now. But some of them are also appropriate for Colorado, Sackung, and for bald eagle. And then lastly, I think it's always a question that we have, what is the potential for these big, deep, slow movers to fail catastrophically from a variety of different forcing events? And I think one of the best examples of why this is really important, and it's something that's driving our USGS landslide program right now in terms of finances anyway, and science, and that's the Barry Arm landslide or landslides in Prince William Sound, Alaska. So let's step back a minute and just talk about where we're at here. The town of Leadville is over on the right-hand side here. The ridge we were just looking at is right here. The trenches are in this location. This is the Busk Creek Valley. The trim line is in a steep kind of area, maybe 2/3 of the way up the slope, and I'll point that out again, or at least it's a zone where we think the trim line is located. This area is also the northern end of the Arkansas River Valley and the Rio Grande Rift. And the reason I bring that up is because a lot of times earthquake shaking can cause movement of these saccung. Work by Cal Ruhlman and Carl Kellogg and others have pretty much shown that there's no documented Holocene or late Pleistocene surface displacement from earthquake and fault activity. So for late Pleistocene, to me, that means, there hasn't been much surface rupturing, any surface rupturing from earthquakes for the last 100,000 years or so. For those of you who are into 14ers, Mount Massive is just south of our site here. And you have a nice view of it when you're out in the field. All right, a little bit more about geology. The nice thing about bald eagle is the geology is pretty much consistent, and it's all Proterozoic St. Kevin granite. It's YGS on this map. It's this light pink stippled unit. The valley bottom, this is the Busk Creek Valley bottom. It's covered in glacial till, Pinedale till, from 22 to 13,000 years old. And it's up also on the valley walls here, at least on the northwest side, and a little bit on the side where Bald Eagle Ridge is. And the other thing that both Carl Kellogg and Cal have kind of shown is that they show quaternary landslide deposits pretty much along almost the entire extent of Bald Eagle Ridge. And you'll see why they do that when I show you some of our detailed topography and photos. All right, I need to really tip my hat to a bunch of people, and the first two that I need to do that with for starting the work here are Dave Varnes and Dorthy Radbruch-Hall. They're the two, along with Bill Savage, who initiated field work and periodic surveying of monuments at Bald Eagle in 1975. So they had the foresight to start surveying, but then they had momentum to keep going into the next century. And then we were able to pick it up. I started at Bald Eagle in 1997, about halfway through this study period. And let me say one more thing here. From my conversations with Dave when he was still with us, it sounded like Dorthy was the first one to get interested in Sackung in Colorado and other places too. And then she kind of recruited Dave to work with her on a bunch of different sites, primarily in Colorado. And then also Bill Savage got involved. And I think the three of them in the late 70s were the primary drivers in the US of research into these features. I will say in Colorado, the other person who has kind of kept this work going forward is Jim McAlpin, who's worked on Sackung in Colorado and many other places around the Western US. These two papers were really the first got people's attention with regard to Sackung and Sackung in the US. And the first is a professional paper by the three people that I mentioned there. And one of their primary sites that they included in this paper was Bald Eagle. That was published in 1989. And then they followed up in 1990 with the first open file that described their initial surveying results from monuments that they repeatedly surveyed at Bald Eagle. Also need to tip my hat to everyone who's come after Dave and Kathy and Bill, and that's a long list of people. And I'm not going to read all these names, but I'm sure that the group will notice some names that they recognize in this list. And this is, I mean, a big thanks to folks to repeatedly hauling survey gear up to the top of the ridge and putting up with some pretty lousy weather sometimes, as is shown in this picture. This is Nikita Avdievich and Olivia Hawk, and they were with me up there this past September on a great field day, but a truly miserable weather day. So additionally, I do want to thank Bill Schultz and Rex Baum for chatting with me within the past week about some cross sections that I'm going to show you today. And Vince Matthews, of course, for his enthusiasm for Sackung and encouragement over time to keep this work ongoing. And then, of course, Jim McAlpin, who's done a lot of other work at Sackung sites in Colorado and the Western US. So my outline for this presentation today, I'm going to summarize previous work. I'm going to update the survey results. The last results we released in a USGS open file report in 2000. And we have new data from after that, from 2012, 2013, and then 2022. I'm going to present some new 1 to 1,000 scale structure mapping that was recently completed from pretty newly available lidar data, and present some new measurements of discontinuity data, fracture orientation data, essentially, that we collected within this past year, and talk a little bit about rock mass quality as I'm talking about those fracture data, and then integrate all these data into an couple interpretive cross sections that kind of show the overall ridge deformation. And then talk a little bit about the implication of the results that I've presented, or implications. So in terms of previous work, this map on the left is from the Varnes, Radbruch-Hall, and Savage professional paper. It shows how they mapped Sackung features in the late 80s. And the red features that are shown here, those, hopefully you're seeing my mouse, those are the trenches that I've been talking about, which one of them was showed on the title slide. I think it was this one right here. This red line is the Pinedale trim line, which defines a kind of an oversteepened part of the mountain slope. And then these other red and black lines, the red lines are they clearly identified as ridge spreading features, and the black lines as lineaments probably related to ridge spreading. And what they had available at the time, primarily in the late 80s, I think, were 1 to 24,000 USGS topo maps. And what they were able to do with that, and I think including field work to make this map, was really, I think, quite amazing, because when you see the maps that I'm going to show you here later on, they look a lot like this one, just with more detail, because we have lidar data. This cross section here shows from the same professional paper. It's not actually a cross section from bald eagle, but it's kind of an idealized cross section of the main sense of motion of these features, the uphill facing scarps and the ridge crest graben. And we're gonna try to update and convince you today that we have some evidence to be able to make that cross section a little bit better, because we have new data that we're using that provides a little bit more detail. This cross section down here on the lower right, that's some modeling from Bill Savage, some plastic flow. That's a plastic flow model of deformation of a bald eagle type Sackung. And what you see here is the graben is well represented. The uphill facing scarps are well represented. But what we really, they didn't see at the time, and I'm hopefully going to convince you today that we see these now, are these compressional thrust features down at the bottom of the valley. I think I see several areas where there are structures that probably represent that compressional flow that they didn't see at the time when they did the original work. Okay, this is the original network of survey points from 1975 that extended to both sides of the valley. Again, the trenches and graben on the Bald Eagle Ridge are here. These points are on the opposite side of the valley. And they did this original work with a theodolite and an EDM. And of course, back then, you needed line of sight to do pretty much everything. GPS wasn't really around yet. And in order to be able to survey these points on this side, they had to shoot them from the opposite side of the valley. And that's why this network is spread out as much as it was. And what we did when we started doing GPS work in 1999 is we really limited, we didn't need line of sight anymore. So we didn't have to survey the points on the opposite side of the valley. And these are the points that we did survey, the original Varnes points. And we kept using this stable base station, 0.4, that you'll see repeatedly, the same as was done in the original survey work. There's another point just to the south here called point K, and we, as well as 0.6, to kind of confirm that our base station was stable and is stable still. I'll show you those results in a second. In 1997, we added some supplemental points, and the reason we added these points was to try to get a better handle on any kind of differential motion within the area of these trenches. And we've surveyed those, I think, 5 times since 1997, and you'll see the results from those today too. So this is the my evidence that 0.4, our base station, is stable. And the way we did this was by repeatedly surveying point K and 0.6 with respect to 0.4. And we repeated these, the 4 to 6 baseline and the 4 to K baseline, every time we were there. And we periodically repeated this K to 6 baseline. But these baselines have not changed since I've been involved for the last 25 years. And what I'm showing you here at the bottom are the positions of 0.6 and point K. And these error circles that you see here, those have a diameter of 3 centimeters. I really need you to note the scale. The scale is 1 centimeter. The x-axis and the y-axis are scaled the same. And the divisions there on each axis are 1 centimeter, and the error circles are 3 centimeters. And if you look at the results from point 6, for example, you could fit all of those points within one 3 centimeter error circle. So I'm convinced that point is stable, but also that baseline is stable, suggesting that point 4 isn't moving with respect to point 6. And the same goes for point K, although the spread is greater. Here you could fit all of those points except one within a 3 centimeter error circle. And yes, there would be one point that would fall outside, either 1982 or 1987, but I'm calling that good. So some updated survey results from actually the moving points. This is point 3. I pointed this out in the one photograph. It's right above this kind of oversteepened trim line area, just below downslope from the lowest elevation uphill facing scarp. This point, as you can see, since 1977 anyway, has just a beautiful trend line in terms of movement. Again, you see our error circles here, 3 centimeter error circles, but that trend line is pretty much, I think you can hang your hat on that point is moving. With the exception of 1975, I'm not sure what happened in that year, but I'm going to show you some movement rates here, and they're all going to be with respect to 1977, and including the 45 years instead of 47 years. That would be the case if we use 1975. Okay, this is let's see. Oh, one more thing. This is pretty interesting. This shows a period, first 10 years. And after that first 10 years of survey results, Dave wrote that there's no movements in excess of the expected surveying errors that have been detected. And I think he may have said that because of the results from 1975. However, luckily for us, he kept going back, and he went back again in 1989, and then we followed up again starting in 1997. Because if he had stopped right then, we wouldn't really know that movement was ongoing, because he wasn't yet convinced, based on surveying errors, that he was actually seeing a signal. This is just breaking down. It's the same graph, just breaking it down into a movement rate. And the main things that I want to point out here is that from 77 to 89, it was moving about 7 millimeters a year. There was a period here of no movement from about 9, and then it picked up again after 99 to this year. But overall, the movement has decreased from this first period to the second period. It's now moving about 3 millimeters per year. Overall, in the whole 45 years, it's also about 3 millimeters per year, taking into account the 7, the 0, and the 3. So it's still moving, but it appears to be decreasing, and it also is episodic. It's not continuous. This is the vertical movement of point 3, which is also pretty convincing in terms of a trend line. Even those error circles for elevation with GPS, I made those error circles 6 centimeters in diameter, and that's partly just based on repeatability and experience in kind of imperfections and leveling imperfections in using different antennas and phase centers of antennas. So I was generous with the error here, but that trend still shows up nicely. The point is moving to the northwest horizontally and then downslope vertically. This is point 1, just on the downhill side of the Graben. It's also moving, not as fast as point 3. We look at the rate here, 5 millimeters from 77 through 82, and then about 1 millimeter per year from 99 through 2022. It also had a period of no movement, a little bit of a longer period than 0.3. I think the point here is that the average velocity of 1 millimeter per year is about a third of the velocity of 0.3 down just above the trim line. This is 0.2, and one thing to note here, this direction of movement is kind of cockeyed compared to everything that we've seen so far. Instead of being to the northwest, like 0.3 and 0.1, this is to the southwest, about like that. And if you notice, apparently this bend in the fault at the edge of the graben, apparently that bend in the fault is enough to make a difference in the movement direction of 0.2. It's not moving fast, and you can make the case that it hasn't really moved since about 1989, but it did have a period of movement, at least from 77 to 89. And if you average that over the 45-year period, it's about a half a millimeter per year. This is an average velocity of about 1/6 of the velocity of 0.3. So 0.3 is really the point that's really moving a lot here. All right. Oh, I wanted to show this again because I'm going to show the results from the supplemental survey points. And again, in the red circle, those are the supplemental points. And we were hoping to see some differential movement between the trenches. And unfortunately, we really didn't see much differential movement until you got right down by 0.3. So 0.431 is up by the graben. And as you go down slope, you end up just above the trim line at 0.438. 0.438 overall is moving about the same rate as 0.3. And the rest of the points are just gradually kind of creeping along at about 1 millimeter per year. Overall, during that 1997 to 2022 period. However, when I last did this in 2013, after our last survey, the velocity then was about twice as much as we see here now for points 431 through 437. So the reason I'm saying that is because these points are also decreasing in movement with the exception of 0.438. So what are some possible reasons? Well, these results are precipitation and temperature records, long-term records from a SNOTEL station, the Brumley SNOTEL station, which is about 19 kilometers south of the Bald Eagle study area. And the elevation at this station is about the same as the Buss Creek Valley bottom below the trenches, downslope from the trenches. So I picked this station because it had a long record and the elevation was kind of close to where I needed it to be in terms of to have a representative record of meteorological data. So what you see here, if we start at the upper left, the black dots are just data, and the blue line is just a best fit line to those data. And of course, the R squared here is not good. But I put that line anyway on there because I felt like it's representative for what you kind of crudely see with your eye. And it suggests that precipitation is decreasing. And this is precipitation in this case includes both rainfall and snowfall. And if we dig into that a little deeper and we start looking at the snow water equivalent, which is just the amount of water in snow, and we look at that through time. So each black dot here on the upper right is just a year. And this is on the y-axis is the maximum snow water equivalent. And on the x-axis is the date when that maximum is reached. And so you can see that when you have dates late in the year, late April and May, where your maximum snow water equivalent is reached, that those years always have more water from snow. However, the problem is that when you look at snow water equivalent by year, instead of what you see is that the time of maximum snow water equivalent, or the date, is actually becoming earlier. And for anyone in Colorado who likes winter sports, this probably isn't a surprise. And this whole slide isn't a surprise to anyone paying attention to climate change issues. This is a high altitude site, and there's dramatic changes happening at these elevations in Colorado. And I think this slide kind of portrays that. So the snow is contributing less to precipitation every year. That's what this chart suggests. And then, of course, when I first plotted this up, the lower right here, mean annual temperature, it's rather shocking how much that has increased since 1981, just in a matter of, about 40 years. I don't think there's any trend line needed there. And as I say at the bottom, this is possibly a good news from a deep-seated landslide hazard point of view, but it's certainly bad news for everything else that we care about. Anyway, the point here is there's less precipitation, and there's a trend of decreasing precipitation and a trend of increasing temperature. And this could be a reason for the slowing of movement at Bald Eagle. All right, I'm going to talk briefly about the new mapping that has been done in this past year, mostly actually within the last few months. I'm just getting you oriented here. These are our survey points that we've been talking about so far. This is lidar data that you're seeing, 1 meter lidar data. And the trenches, of course, show up really nicely here. And you kind of get a feeling right off the bat that just looking around that the trenches are not the only features that are showing up here because of ridge spreading movement. And we'll see that when I pull back on the next map I'm going to show you, but you already get a feeling for it here. I'm going to just step through the things that I've mapped. And these, of course, are just normal fault scarps. The trenches, of course, pretty easy to map. I used slope when I did this, so I actually picked the break in slope to map these scarps on. This normal scarp here, that is the top of the trim line zone, which is right here. There are features scattered all over Bald Eagle Ridge that I can best describe as benches or troughs. And I was reluctant to map those as scarps because it's pretty hard to map a scarp on something that looks like that. These are just a couple representative cross sections through those benches and troughs. And you can see on the left here, it has the look of a road cut, except there's no cut and there's no fill. There's a constant slope below and a constant slope above, and then a bench. In some areas, there's more of a trough, but still a constant slope below and above. And you get and this is my interpretation, I think these are probably incipient scarps. And if I were forced to, I could map a scarp right here at the crest of that. However, so far, I've just mapped all of these as benches or troughs, which show up here as purple. But these are scattered throughout the whole ridge. This is what one of these look like on the ground. And this is, again, as I said, it looks like a road cut, but it is definitely not a road cut. This is the version, just pretty much the bench version, not the trough version. Lastly, these purple lines down at the bottom of the screen there, they are what's been mapped on the geologic maps as true tectonic faults. And I want to point those out because they truly do kind of have a different nature to them. They're much more linear. They tend to be longer than the fault scarps related to Sackungen features. Okay, this is the pulled back view of the same area. The area we were just looking at previously is right here. Those are the trenches. The fault scarp mapping. Again, the thing to note here, as you proceed to the northeast, these fault scarps actually drop below the trim line. So the ridge spreading is actually happening here also below the trim line, unlike over here where it's mostly just above the trim line. The other features to note here are kind of our classic landslides that we're all used to seeing. These are pretty impressive features over on the other side of the valley. And unfortunately, I can't tell you much about those because I haven't really looked at them in the field, but they have beautiful scarps. And in a minute here, you'll see that they also have beautiful toes. And I think they're probably bedrock involved, but I can't say that with too much confidence yet. Again, here are the benches or troughs. All throughout the whole Bald Eagle Ridge. It's not just the uphill facing scarp area that we've been looking at through time that's moving. Well, at least that has moved in the past. The whole ridge has moved in the past, and these benches are reflective of that. Again, the more tectonic fault related features, or at least lineations. And then the toes. One thing about this area that's really pretty interesting and could be really meaningful for trying to interpret the big picture of what's going on here is there are a lot of rock glaciers up valley from where we're at here. These are some here where I'm pointing out with my mouse. There's more over on this side of the ridge. And those imply that there could be at least ice within the core of those rock avalanches, possibly permafrost within the ridge itself. It's a controversial topic in Colorado. We don't know if it's the case or not. But the rock glaciers, they suggest at least there's probably been ice in there in the past. And we don't know if they're moving or not either. That would be helpful to know, and we don't currently know that. I mentioned this before, but I'll mention it again, particularly for the toes down here at the base of the slope. The slope map really came in handy. Here the yellow colors are shallow slopes and the red colors are steep slopes. And these toes, as landslide toes are everywhere, they're pretty subtle when you're standing in front of them in the field. They show up, at least I think they show up pretty nicely in the lidar right here. I'm convinced that's a toe. I'd like to go back and look at it in the field now that we've seen it in the lidar. But at this point, I'm convinced that that is the toe right there for the entire slope failure or spreading that's going on at the trenches in this direction. And I'll show you a cross section of that in a minute that will hopefully support what I'm saying. These toes in the talus or rock avalanche deposits, in my opinion, those are just from a different style of deformation than this big deep-seated toe here and the big deep-seated toe here. Last slide related to this map, these yellow dots are areas that we went to in September, and we measured fracture sets, the orientation of fracture sets. We did some rock mass quality ratings, and I'm going to show you those next. So if you have this map in mind, there's 9 different sites there. And I'm just going to show you a couple of those sites to give you a feeling for what the rocks look like. I'm not going to spend a whole lot of time on that. So this is one of the sites on the southeast side of the ridge. There's 4 distinct fracture sets here. You know, the beautiful thing about this granite is the fracture sets are really pretty easy to see, at least at this outcrop. All of these sets are dilated. There's an adverse set that you can kind of see that's dipping out of the slope towards us. The view here is to the west. And What we don't see here are any features that are really the same orientation as the ridge or these uphill facing scarps. And we're partly biased because of our view here. We may not have a good angle to see those fractures. But I'm going to step you through what we do see here so you get a feeling for, if you're not used to these lower hemisphere equal area diagrams, these are poles to planes. When you see poles around the outside edges here, that means that's a steeply dipping fracture. When you see them towards the middle, that's a shallow dipping fracture. The strike of these is 90 degrees, that pole. So for this red dot, the strike of that would be roughly east-west. And I'm just going to step you through these steps to give you, or these fracture sets to give you a feeling for what we were mapping. That's the high angle set, almost vertical, trending east-west. Another high angle set, but not quite as steep, trending the same direction. The set that's basically 90 degrees orthogonal to the first couple sets, trending pretty much north-south, a little off north-south. And then lastly, the adverse set that's dipping out of the slope. I'm showing you these, but really, I don't think any of these sets at this exposure are major players in what's going on in this ridge in terms of the deformation that we're seeing. The other thing I want to mention here, for those of you interested or familiar with rock mass quality, we collected enough data to look at these various different schemes, the RMR scheme, the Q scheme, just basic RQD, and then the GSI scheme. The rocks here, in terms of a qualitative description, they're not really very poor rocks. They're moderate. They have a moderate to fair rock mass quality, and that's pretty much the case across all of Bald Eagle Ridge. This is another one of our sites. This one is right over kind of a outcrop within the trim line zone, below the steepest scarps. Here we do see a set, these red lines, which is highlighted on the stereo net, dipping to the southeast and with a strike to the northeast, the same orientation as the ridge. At other sites, we see a steep angle set, a moderately angled set like this one, and then a shallow set down here on the stereo net. These are the fractures, I think, that are directly involved with this ridge deformation. The trend is pretty much right along the ridge in terms of their strike, and there's enough variability in their dip to kind of be able to do a lot of different things with that. And I'll show you what I mean in our cross sections. All right. These are data from all 9 sites. And again, the trend of the ridge is north 40 to north 50 east, represented by this line. And the fracture sets in this box are normal to that line. And as I was mentioning, you have steeply dipping fracture sets, moderately dipping, and then shallow dipping along that strike direction, both to the southeast and to the southwest. And the southeast set is nicely represented when you just plot everything up in terms of a rose diagram. The southeast dipping sets are actually the ones we see the most often when you look at all the different sites around Bald Eagle. Okay, this is just the first cross section that I want to show you. This is A prime, so it's going right through the trenches, the big trenches where we've been surveying. I've included a toe down here at the bottom, which we haven't seen in other cross sections of Bald Eagle before. And I've used our fracture sets, which you can I just described, and you can kind of see in light gray here, to kind of constrain what I did with this basal slip surface, as well as these faults that control the uphill facing scarps. This ridge is really, at one time, it was fairly flat topped. Of course, this side where I've got sagging labeled. You can visibly see the sagging of that ridge when you compare it to this side. This bulging right here is just the rock glacier bulging, but there's a bigger area of bulging that's related to this basal slip surface, I think. One thing that I kind of realized when I was talking to Bill Schultz and Rex about this cross section was that really this is the graben that we've always recognized up here at the ridge top, but all these other features are really grabens too. So there's a kind of a nest of grabens that's responsible for the sagging. At least that's how I'm interpreting it. And point 3 here, of course, is the point that's moving the most. So it's slowly moving downhill, and the area behind it is sagging behind it. One thing that Rex mentioned when I talked to him, there's this part of the basal slip surface. It's pretty steep, so it's providing a nice driving force for everything that's happening down below it. But at this point anyway, point 3 is the point that's really moving towards the valley bottom. All right, just to show you a couple field photos to maybe convince you a little more. This is the area of the talus rock, possible rock glaciers. That's right here. And that toe, if there is one, is down here, more down at the valley bottom. But when this is looking up Bus Creek, Bald Eagle Ridge is on this side. When you look at that area, you think, okay, that could be bulging. At least that's what I see when I look at it. This is looking straight across at it, and you kind of get the same impression when you have that view of it. This is cross-section B prime right here. Pretty much the same deal, except these small features, those were the benches that I've mapped. I haven't had the courage to actually draw a fault through there, but I do think they're representative of spreading, but maybe not through going faults at this point. Comparison with other Sackung cross sections. This is a good match, of course, but I'm convinced that this cross section kind of is based on the type locale of Bald Eagle. So I would expect a good cross section there. This is more representative of the benches, just general spreading. And then this is a best match, which is actually from a German PhD thesis in 2000, Stefan Weidner. And he pretty much, that cross section to me looks a lot like Bald Eagle, even though this was just a hypothetical cross section that he put together. I'm going to speed up here a little just so I don't go over on time. Okay, conclusions. Ridge spreading and sagging is ongoing. Movement is episodic at rates of 1 to 4 millimeters per year, but seems to be decreasing, possibly due to warming and drying. Movement is largest at the trim line where the tallest scarps are located. Structural mapping indicates varying style of deformation along the ridge with nested graben toes and a basal slip surface. And then the other piece here is that long-term observations were really required to understand this movement. After the first 10 years, the results, as stated by Dave, were inconclusive. A few implications, speculation. Given the movement's been very slow for almost 50 years and appears to be decreasing, seems pretty unlikely to me that this ridge will fail catastrophically, at least due to climatic forcing conditions. And the other piece here, if we assume that this movement started after the glacier withdrew about 13,000 years ago, and we use this rate, we get about 13 meters of movement near the graben, 53 meters near the trim line. These displacements, when you put those I've plotted them in Google Earth and looked at them in my cross sections, and it seems pretty reasonable that that is the case. That it could have started after the glacier withdrew, but we really don't know. The other piece there is the work that Jim McAlpin did over by Aspen Highlands. I think his rate of movement there was on the order of 1 to 4 millimeters, if I've got that right. And also he had that from trench work he had that starting after glacier withdrawal. One thing to consider with these cross sections, there may be nested grabens in features at other Sackung sites that might be considered when developing cross sections. And an example here is Berry Arm. Some of you on the call know this map. There's a lot of downhill facing scarps up here, uphill facing scarps through here. It's pretty, I think, pretty reasonable that there's an overall structural graben in that location, and that these uphill facing scarps probably sole into a basal slip surface and actually reflect kind of a nest of grabens. And with that, I think I will just stop with references and stop there. Thank you.